Hello, my name is Anar Smith. I am a third year student at the University of Oregon, and this is my video explainer number 2 for Physics 413. All right, and moving on. So our problem today is in 1997, physicist Andre Diem claimed to levitate a live frog in a magnetic field for 30 minutes. Evaluate this claim critically. Was this an April Fool's prank or does this claim seem valid? And there's 4 parts to the problem. All right, so first for a little bit of background, Andre Diem is a physicist working in England in the School of Physics and Astronomy at the University of Manchester. In 1997, he managed to levitate the frog, and he was awarded the 2000 IG Nobel Prize. This is like a fake Nobel Prize nomination for kind of joke experiments. And then later in 2010, he won an actual Nobel Prize for research on graphene. We're also provided some potential useful information for the problem, such as the gradient near the opening of a strong short solenoid can be approximated as the gradient of the B field squared equals B field squared over L, where L is the length of the solenoid. So this automatically gives us a hint that a solenoid is going to be involved in this problem when it comes to levitating the frog. And then, and additionally, we're giving some typical magnetic susceptibilities, gold, silver, copper, water, etc. And you can all notice for most of these, they're all negative. A couple are positive, but they're all very small numbers. So for part A, we're asked, how would Guillaume have set up this experiment? Include a drawing. So I think that there's a couple things that are important for this problem when setting it up. First of all, the frog needs to not be able to move. That just makes it easier not only to work with the frog, but to place the frog above the solenoid. As I said, it's easiest to use a solenoid of wire, which all solenoids are made of, but it's also hinted in the potentially useful information for the problem. And the solenoid, I believe, should be bigger than the frog or the same, or have a diameter to which the frog is entirely above the solenoid. So the solenoid isn't so small that just like a small part of the solenoid is beneath the frog. So what it looks like, you can see here on the left, there's our frog. I personally hope the frog is sleeping. That's one way to help make it not move. Additionally, you can see in the blue there is some sort of, but maybe like a glass tubing or something, just to help keep the frog right above the solenoid. In case if for some reason, the frog isn't perfectly balanced or weighted in the middle, that way it doesn't end up falling off of the magnetic field of the solenoid. And on the right hand side there, you can see we have a current I, we have a length of the solenoid, which is drawn at the bottom of the figure, a distance D between the solenoid and the frog, a B field that is going to be pointing up towards the frog, and not only the Z's representing the frog is sleeping, they also show the positive Z hat direction for the problem. So part B asks what conditions would need to be satisfied in order for the frog to levitate. So first of all, is I think what we mentioned in part A is important. Additionally, diamagnetic materials are repelled by magnetic fields. This is because of their electron structure. So the frog will have to be a diamagnetic material in order for it to be levitated by a solenoid. If the frog is a paramagnetic material, which is the opposite of a diamagnetic material, it would actually be sucked into the solenoid, the opposite of levitated. So for part C, we're asked perform a back of the envelope calculations, include a clear explanation of your thought process, and list clearly any assumptions that you make. So the first assumption that we're going to make is that the frog has a magnetic susceptibility less than 0, and is therefore a diamagnetic material. That way it'll be repelled by the magnetic field and it won't be attracted towards it. So there's a couple things here. So we know that the force due to gravity is equal to mass times the acceleration due to gravity, otherwise known as g. We have the force of a solenoid, which is given by the magnetization times the gradient of the B field created by the solenoid. Then we have the energy of the gravity and the energy of the energy produced by the magnetization from the solenoid. And we're also given that from the potentially useful information that the gradient of the B field squared is equal to the B squared over L. So using energy, we can see that the energy total is just going to be the addition of the two parts that were defined in the last slide. And we can set, like setting this equal to the force, because we know that it needs to balance out to be 0. We can actually find that we get the negative mg e sub z, where e sub z is just a unit vector pointing in the z hat direction, and minus X, big X is actually chi, which is the magnetic susceptibility factor, times the volume of the frog all over mu naught, and that additionally multiplied by the B field squared over L. And B of R is just representing the B field in direct relation to some point, which would be where the frog is located at. And with this being equal to 0, we can actually solve for one value. Like, for example, we can solve for chi if we happen to know what the B field and the length of the solenoid is, as the and mass of the frog, volume of the frog, etc. Using force, however, we can actually find the equilibrium, which is that's the equilibrium condition is going to happen when the force created by the solenoid is going to equal but be opposite to the force of gravity. So we can set the two just directly equal to each other. And if you follow through the math process there, we actually get that the B field squared over L, which is the length of the solenoid, is actually equal to rho, which is the density of the frog, times G times mu naught L over chi. So in conclusion, with our two conditions that we found from our calculations, what additional information we would need to verify Andrew Guillem's claim is the dimensions of the solenoid that he used for our basic calculations that we created from part C. This is not a complete picture. Again, the question at the very start of the question we were asked, is this an April Fool's prank or is it valid? It's very valid, but again, it depends on the conditions. For example, at very low temperatures, there's such thing as superconductors, which have a chi of -1, which is a very, very large number of chi, but they're capable of levitating quite a series of objects. And it's very possible. The question is it possible to do it with a living frog? And is it, So anyways, thank you so much for watching. Here's are some of my sources. Introduction to Electrodynamics by David Jigger Griffiths is our textbook for the class, and the other ones are some research papers founded on the project by Andrew Guillem. So yeah, thank you so much for listening. I hope this was informative. Bye.